Hello and welcome to the Gaming with Science podcast, where we talk about the science behind some of your favorite games.
Today we're talking about Periodic by Genius Games. Hello, welcome back to Gaming with Science. This is Brian.
This is Jason.
And we are joined by Dr. Raychelle Burks. Raychelle, could you introduce yourself, please?
Yes, I am Raychelle Burks. I am a chemist and a forensic scientist.
Ooh. Well, I'm so glad you're able to join us today. We were just talking about, let's see, you said that your Instagram handle is radium yttrium and you're Dr.
Yes.
Rubidium, and this game is all about the periodic table. You use three different elements in your sort of social or media, like internet handles. So I think we got the right person for this.
I hope so.
And just to give a bit more information to our listeners, you said you're at American University in Washington, D.C., right?
Yes. And actually it's funny because it's like, it is American University. What a wild name for a school. We have a lot of universities, but it is one that's kind of got a congressional mandate. There was, back in the day, they were like, we are going to have the American University. And it's like, it didn't quite work out, but...
That's interesting. So you said there's a congressional mandate. So this is kind of like, we're at the University of Georgia. We're a land-grant institution. So we sort of have this mission that the university is supposed to satisfy. You were in a similar situation.
It's weird. I went to a land-grant institution, so I'm a proud Cornhusker. That's where I got my PhD. So University of Nebraska at Lincoln. And so land-grant institutions, definitely a bit different, right? Because you're taxpayer money, there's some property involved, and you have a mandate. You have an extension office. Mm-hmm. I believe you have a fantastic extension office. I think all state residents, have the ability to have like a library card and come to a university event. Like there's a real community kind of based thing. And in a way, American actually also has that. Many universities do, especially for the neighborhood they're in. But American University is actually chartered by Congress, like way back in the day. I think it's 1893. Is this a pop quiz? No, but so it's an interesting history that kind of comes about.
Well, very cool. Let's see. So we're here to talk about the game Periodic by Genius Games. This is another in our Genius Games roster, which I figure eventually we'll be working our way through all of the Genius Games at some point or another. But this is our second chemistry game. So we're excited to talk about it. But really, this game is about the periodic table specifically, which is very cool. And I definitely have questions. So I'm excited to have somebody here to give answers. But why don't we start with our science banter topic? So what have we learned or found, studies, something interesting in the world of science today? So we usually let our guest go first if they've got something. If not, Jason has something queued up.
Well, as a forensic scientist, I will say I spent a lot of time kind of in crime, right? I mean, hey, what can you do?
Makes sense.
And so,
so does the show CSI drive you insane? It must.
No,
right?
You know what? It's because I know it's fiction. And there's a lot of I'm sure, if you ask an astronomer or physicist, it's like, oh, does this show drive you? I'm like, there's some good bits. There's some bad bits.
Sure.
I would say if anything, it'd be like Breaking Bad, where you're like, the one time we've got a full-time chemistry show, it's a meth cook.
Well, crime, there you go.
But I would say one of the stories that I came across was, we see some of the same elements as kind of like culprits, right? People are like, sure, arsenic, like we get, thallium, right? People are very familiar with that, not only because of news stories, but because of kind of historical crime fiction. I mean, if, you've seen Agatha Christie, you're like, is it going to be arsenic? But there are other elements that you're like, excuse me? Like you mm-hmm. don't see them as often. So it just seems really wild. And it really caught my attention. I came across a story involving molybdenum.
Molybdenum? Oh wait, it's not molybdenum? Have I been saying that wrong my entire life?
No. It's don't because I will pronounce things as I like them.
Okay. I think in biology we usually say it's a molybdenum cofactor. I've never heard this other pronunciation, but I'm going to start using it.
And that is my new and exciting way to say it. But yeah, don't go by me because I will also, in a weird way, I went to a year abroad in England in college, and I will actually say aluminium. But to me, it helps me actually remember how to spell it. I mean, it makes sense. Au, mini yum, right? So when I pronounce it molybdenum, that's literally to help me remember. Oh, it's Molly, a B, a D. Like, because I'm like, I love how they spell these elements sometimes where it's just wacky. Well, for us English speakers, we're like, did you really put a Y, a B, and a D like right next to each other? But to have we just don't hear about this element a lot, right? And, even though, of course, like a lot of your metals, the kind of shared impact, kind of quote heavy metal poisoning where you're going to see the same types of symptoms. But it's like the same old heavy metals, like lead, like you're
lead, mercury, arsenic.
Yeah, it's the usual suspects. And that's why this was like, it's like a twist in a Dateline episode where you're like, you mean it wasn't the husband?
So this is
what?
So what happened with it?
Yeah. What was the story?
It really kind of affected cattle. And that's the thing is this wasn't a human poisoning. Is that some of the features, your GI distress, joint pain, that should sound familiar to folks that kind of clock some of these metallic poisoning things. But there's also a big part of crime that involves like wildlife related. Like people will actually like try to hurt each other's cattle or try to poison crops, right? Like sabotage level tomfoolery. And so it was about, the real impact of this on this livestock. And then how did they kind of map it out and kind of get to the root of things? And so that kind of a crime, sometimes we're so focused on human involving action, which I understand why we all do, but to just see how they apply the same type of toxicology work and like sleuthing to be like, who is poisoning these cows? Like, was like really interesting to me. But again, also because it's just an element that, I mean, it's just not one that we talk about. It's not, one of the most... when we talk like biologically, you're like, yeah, it's the same 7 elements. Okay. A lot of time on carbon, a lot of time, on, then you got the coinage metals and you're like, sure, snooze fest. But when you hear something that's like an element that even you forgot about as a chemist, is kind of like,
I'm trying to think. So there's a surprising number of elements, the micro trace elements. You need like selenium, and you need a little bit of cobalt, and you need, I think you probably do need a little bit of molybdenum. And there's a couple of, what else am I forgetting? What are some of the weird ones? You need some zinc. You need a little bit of copper.
Oh, you need plenty of zinc.
Yeah.
You need
copper,
you do? Not too much.
All right.
Not too much. But selenium, the fact that you said that is another one where we know that it's got some real positive benefit, right? Biologically. So sometimes people will take, and they hear this, they hear a snippet in the news of, usually it's some type of, trace element that is important from a tallow point, and like the research gets interpreted as being like
they poison themselves. They completely overdo it.
They a little bit go too far. And as we know, too much of good thing is actually bad.
Yeah, that's the classic human thing. Well, if a little is good, then more must be better.
The dose makes the poison.
And also sometimes dose makes the poison, but also sometimes unit conversions. We know, right? If you're talking about quote micron.
Yeah, what is a microgram anyway?
Right. But then somebody's like, oh, they dispersed a milligram.
Ooh.
Yikes.
I think having the mu symbol in the metric is probably bad because have you seen this where people will use the symbol font and then everything gets converted over during the process of like interconverting a document, and your little symbol font mu turns into an M, and all of a sudden your microgram is a milligram.
Yep. And you can see how it happens, right? And then it's like, oh no. And it is this, it's unfortunate. It is an accident. It is a mishap. And people, sometimes they're trying to do the right thing. They think, oh, I gotta take my daily vitamin. I'm taking a bit of extra, whatever. And you can go too far. That's the story of the periodic table. Okay. You can, in fact, go too far.
So let's see. So the story was some cows got heavy metal poisoning from molybdenum, right? Is that this was a news story?
No, I found it in a journal article.
Oh, that's cool. Can you share
But
that with us?
I also go looking for these things.
Sure.
So you're like, yeah, I just casually came across this mass poisoning. Yes, I will share it with you. It is but because of my background again, I kind of look for these things, that says something.
All right. What about you, Jason? Did you find us anything cool?
I did actually something related to this. I found glowing plants. So I've always been fascinated with luminescence, and some of our listeners may have heard about like the firefly petunia, which naturally glows due to a light emitting compound it creates.
Well, not naturally. We had to make this.
Yes, yeah, it was genetically
Yeah.
engineered. This is something else, actually, and it relates to the game because what this group did is that they took a bunch of microparticles, so metallic microparticles, that will naturally absorb light and then re-emit it over a long period of time, several hours, and they injected it into succulents, and they kind of spread throughout the leaves, and they became these glowing plants.
What kind of particles are these? I've heard about these aren't quantum nanodots, are they?
That phrase was not used in the
Okay,
article.
so that's probably not it then.
No, they call them microparticles because they're in about the 7 micron size.
Okay.
It was strontium aluminate. And by tweaking the chemistry or the size, they could change the color. They have this wonderful figure where they show a bunch of these little like succulent rosettes in like red and orange and green and blue. The problem is that you have to inject every leaf individually because they don't spread very far throughout the plant.
Okay.
And they did say that they showed no signs of toxicity in the 10 days that they were following them for the study. So,
I've had plants that have been fine for 10 days without being watered. Okay.
so there's a lot still to do here because this is definitely the sort of thing I can see like, okay, at some point, someone or someone's pet is going to eat one of these. So there need to be some safety studies on those before they get released. But it's still a cool thing because they can make this rainbow of colors. They have this great figure showing the different rainbow of it. And then someone standing in front of a glowing plant wall where they just have a bunch of these succulents up on a wall and they're just kind of glowing.
I mean, that does sound amazing. Is the idea that this is to be a consumer product? Is that the intention?
I think that's the end goal. I think the end goal is that, it's probably going to be a novelty. People keep talking about, oh, we'll make glowing plants to replace lights at night. It's like, I don't think you can actually store enough light in a plant to do that.
Yeah, energetically, that's going to really tax the plant.
So, but they make really cool novelties. So,
Sure. Okay. All right. That is weird and cool, and I'm excited to see the wall of rainbow plants. Thank you for the wonderful chemical stories, but why don't we talk about the game Periodic? Okay, so Periodic is from Genius Games, one of our favorite board game companies, because they specialize in producing games with a hard science theme and usually a strong educational component, although the games are designed to be fun, not educational, because we've already learned how educational is a dirty word in the games industry. So the designers of this game are John Coveyou, who is the founder of Genius Games and has a designer credit on most, if not all, of their games, as well as Paul Solomon, who has designed some Genius games as well as some games for some other companies. He's done not only Periodic, but also Genotype, which we did earlier this season, as well as the game Virulence, which we haven't played yet. Periodic is for 2 to 5 players. We'll play in about 40 minutes. We played way faster than that. I think it's always adjusted a little bit by player count. I think Jason and I had the game done at about half an hour. And that was Jason's first time playing, so probably we could get it done even faster than that if we wanted to, but I don't know why you would. So what does the game look like? The center of the game is a periodic table. Well, it's an incomplete periodic table. The actinides and lanthanides are completely just kicked out. They're not even shown. They're not displayed.
Yeah, those are, for those who don't have that memorized, those are the 2 rows that are always at the bottom, kind of floating off by themselves.
Yeah, if this is the map of the United States, that's Hawaii. It's just kind of off on its own, right?
Well, I have a little pushback about that because numerically, right, that would be like you've removed the Midwest because it makes your map awkward and you shove it down by Hawaii so that it makes it more square.
We just take New Mexico and Arizona and just take them out and just say, well, we're going to put those off to the side somewhere.
Like, here you go.
Yeah. Yeah, well, I hear that there's going to be some discussion about the exclusion of the actinides and lanthanides. Some other parts of the game are you're going to have these group of cards that they say sort of arrange in semicircles around each side. That's not really necessary. You could just stack them up. And each of those are going to represent major groups of the elements. So your nonmetals or your halogens. This is going to be easier to explain when we talk about how the periodic table works. But basically, groupings of elements are arranged around the sides of the board. So the periodic table is our game board. What we're going to be doing is you have your little marker, which is an Erlenmeyer flask, which we've already decided there is nothing more scientific than an Erlenmeyer flask. Across the top of the board, you have a series of cards, and these are your goals. So these are groupings of elements. They can go from 2 to, I believe, up to, I think it's just 3, or is it 4? Jason, do you remember? Are there ever ones where it's only ever 3, right?
The goal cards only have up to 3 elements you need to grab.
Okay. So, and these will be groupings. So, for instance, toxic metals, arsenic and tellurium or mercury or other toxic metals. There's actually 2 distinct toxic metal cards. There's 3 different cards that are based on groupings related to steel. So there's iron and carbon, things that you alloy with steel, and then there's stainless steel.
There's the plant one.
Soil fertility.
Yeah, plant ones, NPK. There were a few that had to do with lasers, some precious metals like gold and silver. And I don't think it was gold, silver, platinum, but there was some that, the ones used in medicine, like lithium, magnesium, and platinum.
Yeah, so they've gone out and they've found sort of groupings of 2 or 3 elements that you can pull together to make some kind of a set or goal.
And I bet this is why the lanthanides and actinides aren't there, is because there's relatively few groupings of 2 to 3 metals that they could put together. And probably also something to do with the way you move on the board to be hard to get to them.
I think it's purely about how you move things on the board. It's like, well, how do you jump down to this separate track of elements? But so those goal cards, they've got little like fruity pebble markers that you'll mark like which elements are on the board and where they are. And the game is really about moving your little Erlenmeyer flask to different places on the periodic table. You want to land on that element. And then you get to collect it. So the way that you move is you can move up and down by going up or down atomic number.
Well, it's okay. You say moving up and down, you're actually moving left and right.
That's a good point. Yes, thank you. You're moving left and right on the periodic table. That is the one that actually lets you wrap around the board and go all the way from the right to the left, because the periodic table kind of has a Pac-Man effect, where when you get to the end of one column, you actually wrap around and show up on the next column. I don't know. Are any of our listeners too young to understand what Pac-Man is?
Oh, definitely.
It's made a comeback.
So other things you can do is you can move up and to the right, and this is called increasing ionization energy, or you can move down to the left, which is increasing atomic radii. Increasing atomic mass or decreasing atomic mass is either down and to the right or
up and to the left.
And that's it. You get these little energy tokens. You pay 1 to do one of those trends. Move your Erlenmeyer flask 1 time. You can pay 2 energy if you want to do a second movement. And you're just trying to collect these elements. You get points for collecting them. You'll have a private secret goal of like, oh, I'm trying to get, a bunch of ones of different difficulties or something like that. The only other thing to contend with is there's 2 ways to finish the game. One is you go all the way through one of those goal stacks of cards of any difficulty. The other is at the bottom, you've got this academic track. So remember, around the side of the board, we've got the groupings of elements. Whenever you land on one, if it's the next one in the series, you kind of move a little marker around, and that lets you move up the academic track.
Whenever you end your turn on one, so it takes a minimum of 8 turns to go all the way around.
Okay. Jason, anything that you feel like I missed?
No, I think that gets it. I like how you described and this isn't our word, we got this from a YouTube video, the little markers that say which elements are the ones people want to be going for right now based on the current goal cards, look like little fruity pebbles. I would nominate those as the most likely piece to be eaten in this entire game, because they look exactly like some little candy.
Yeah.
Like even I look at it, I'm 40 some odd years old. I look at them like, this looks kind of tasty. Like,
is that like you've got a Tide Pod effect for the fruity pebbles?
That's what it looks like. So it's like, definitely this one, respect the age limit on this. Be careful if you're around little kids, because they do look like they should be sugary and sweet.
So let's see. That'll be a new special category for Gaming with Science. Most likely to have pieces want to be eaten. Speaking of which, this is not a very space-hungry game. This gets a high score on the bowl of chips factor. There is definitely room to put a bowl of snacks there. Just make sure that you're not eating the game pieces by mistake. So that is the basics of the game. Why don't we talk a little bit about the science now? And Raychelle, you're going to get a bunch of questions about the periodic table. Is that okay?
Ooh, okay.
So my first question is, what is the periodic table?
The periodic table is, what I say to students is we don't make you memorize stuff, because we put all of the cool information in a single table, and then we literally post it everywhere. Coffee mugs, wall, shower curtain, tablecloths, wall posters. what we would say are these are kind of quote the building blocks, right? And so the periodic table is our quick reference to what are the Legos, the chemistry Legos at our disposal. And it's organized, of course, you have, people learn about Mendeleev and the kind of first, kind of to organize it. Besides the fact that when you look at it, when you really understand how to read any data table, it becomes even more powerful, right? And so to look at it and realize it's organized, why we've organized it the way we have actually tells us something about how the chemicals behave. Kind of organized, you have columns and rows. And if you're in columns, we like to call those families. There's some similar behavior. But we know with all families, there's going to be the weirdo, the evil one. So I look at a periodic table and I'm like, wow, there's some real characters here. There's some real personalities. But with that, you can get an idea of how things will behave and maybe how they'll behave together, what things will avoid each other. And so we've also organized the periodic table. If you go from, say, left to right, you go from metals to non-metals. But then there's the fun hydrogen, right? So hydrogen is in group 1.
Yeah, you're hitting a bunch of the questions I already had.
Yeah, but you have to drop to super extreme temperatures to see that kind of metal behavior of hydrogen. But it is definitely, it is number 1, right? And so we go group 1, number 1. But what you'll see is periodic tables, especially ones that are often kind of posted in places, they try to be like, sure, it's in group 1, but let's put it up. Like float it up here because we don't want people to think that it's gonna, some of the other things in group 1 with the sodium, potassium.
It's not gonna explode when you put it with water.
It's not gonna, and it doesn't have the same type of behavior as some. But then again, it does share behavior where there, kind of ionization energy, where that one electron actually pretty easy to boot, like energetically. The cost is low, and that actually dictates some of the chemistry. But we don't see the same type of metallic behavior at kind of the same operational temperatures. But then again, I would say with families is think about your family members. Do you have shared traits? Sure. But then you always have that one family member who's like, and what are you doing over there? Right?
Oh, yeah. No, I'm thinking about that right now.
So, there's also this interesting thing as you move, down a family. Sometimes like they do this with birth order, which, that's not my area of research, right? But they talk about what's that older kid versus the middle kids versus the baby. And if you go with more like light, medium, heavy, you see that there's some real spread in behavior. Now, families are families. They do have an operating kind of, here's our vibe. But even within the families, there can be differences.
Families are the columns, right?
Families are the columns.
Okay. So let's see. So the periodic table, everything gets an atomic number, and that is based on the number of protons that you have in your nucleus. So, and actually that means that we've talked about this before. For all those people who want to discover new elements, I'm sorry, all of the spaces are taken. The only place to get anything new is at the very bottom of the list because we know everyone has just one more proton.
But, the fun thing is, we have currently 118 confirmed and people are there is some, if you look at if you go to any of your alma maters or people might even remember this from high school, they're like, wait, did she say 118? Because I'm looking at periodic right here and I'm seeing 114 or 112 or 109, right? When you're seeing ones that might be kind of in parentheses or ones, it depends on the age of your periodic table, right? And you can actually see that there's been some exciting updates, right?
Yeah.
And so that's kind of fun to see that. I do want to back up and say, what I love about the periodic table too is, yes, we designate families, right, as being columns. But to carry my kind of human family a bit further, there's the family you're born into, and then there's the family you make. Right? We have kind of circles of circles of kind of affinity.
These are groupings. These are metalloids.
These are groupings, right? Like you can have alkali metal. You can have alkali, or you have earth metals. You have your transition metals, which those are all actually in different families, but they have a big block called transition metals. So it's like we try to say, okay, which clan gang group are you
So
part
they're
of?
still closer to each other in their overall behavior than they are to
Well,
the
right, because you
things
can talk
around
about,
them.
oh, I'm a transition metal
Yeah,
chemist.
yeah,
Well,
yeah.
that's a big group. Which one? Right? Right? Or you can say that, or even an entire field called organic chemistry. You're like, so
It's
carbon,
just carbon.
just carbon. But they don't really mean that, right? They
Yeah,
might be focused on carbon-carbon bonds, but there's a lot of
sure.
other like chemistries involved. But yeah, right. They're really exciting. I love a metalloid. I love anybody who's like, I do what I want. I can be a metal. I can be a non-metal. I
Okay.
adapt, right?
Oh
So
my gosh,
those families are really cool.
we've touched on so many topics I was hoping to cover. Is it okay if I go in with some more specific questions?
Yeah.
Okay. So first of all, if I could just, we talked about a couple things there. Let's start with what are the families and where did their names come from? So in the game, it's alkali metals, alkaline earth metals, transition metals, post-transition metals, metalloids, halogens, and noble gases. Some of those, I guess I get sort of embedded in that question, as you can imagine, is why are there so many metals? And what makes something a metal versus a non-metal?
I mean, I think that that's a really interesting question. I think philosophically, because I have a PhD, and most chemists have a master's or a PhD or a bachelor's. Is that here's where you get to the philosophical part? Is that we try to bend things, and we try often to do it in discrete categories, but that doesn't always work, right? And so what we've tried to do with the periodic table, and notice I am using the royal we. They're like, you didn't have a thing to do with the periodic table.
No, you speak for all chemists. It's fine.
It's for all. Ooh, is, is to find these relationships with chemical properties or chemical behaviors, right? And so we try to say, okay, what are some things that are unique and that group these things together in their chemical behavior, right? And we try sometimes to make those bins too rigid.
Too
We're like, oh,
narrow.
it is a metal, it is a non-metal, it
Yeah.
is a this, and then the metalloids show up and go, really? Are you sure?
We definitely have the exact same problem in biology all the time, where we want things to fit nicely into bins. And you know what? Nature doesn't care about your bins.
It doesn't work. It's a spectrum. And so as you actually look across the periodic table,
Yeah.
you can see this beautiful range of metallic behavior. And then we have things that kind of more fall, if we think of it as more of a spectrum. And we think about things that are more on the metal, like what we think about as metals is like, I'm doing
Iron,
my
copper.
Metallica. But we think about things, that they're malleable, that they maybe conduct electricity. That's not even all metals, right? But we think about what we think
Sure.
is metal behavior,
Okay.
right? And then you go across the periodic table, and like most people, if you ask the common person, is sodium a metal? They'll be like, is this a trick question? What we think of in our mind as being like metallic behavior, non-metallic, and then you have elements that are like, I do what I want. I can, and then what is a non-metal? What do we mean by so you're identifying an element by what it's not?
By what it's not. Yeah, I was thinking about that too. It's like, okay, so some of the traits would be things like malleability, conductivity, would be things that we think of. But the thing is that those definitions are kind of, I know a metal when I see it a little bit.
It is. And then when you get things into groups and you start making compounds, then you can start making things that you're like, oh, but that now conducts electricity or gives off sparks, or we can do fun. Which, okay, then what are we saying is, what are these properties? And then and that's the fun thing about science, is we've kind of got this on lock. But then when we're able to manipulate and build things that you're like, oh, so this now can act like this over here. And that's kind of fun.
I learned recently that there are some alloys that can become magnetic, even if they're made from non-magnetic starting materials.
Right. And so then what does that mean? Like proper, if you define everything by what you think it can do and not do, right? This is the philosophical part that is the grappling of it that keeps, I think, a lot of chemists, when you can, like at the top of the show, when you can think, what is something that blew your mind? When you can read something that you're like, that is really has shaken. What do I understand this thing to be? Right. And that's kind of the really fun stuff, is that even when we think in 2025, we a bit jaded sometimes with scientific thing. But when it comes to the fundamental thing of, but what do you mean it is, that can still blow your mind is kind of fun.
So sometimes in chemistry, you're adding 1 and 2 and you're getting 7.
Which again, loving it for us, because then people think like hydrogen bonding, right? They're like, oh yeah, the interact, whatever. We're finding out new things all the time about this interaction.
Interesting.
And I'm sure in biology, given the fundamental importance of hydrogen bonding to protein structure.
Oh, so like literally the entire thing? Like it's all,
that you're like, what?
Holds together your DNA.
Yeah, and I think that, when I look at the periodic table, even though we try to give it, firm, there are these columns are families and there are blocks and we have this is this. What you actually are seeing is a spectrum of properties and behavior, which gives us a lot of dynamic flexibility, right? And they also just looking around going, well, that explains this wild show that we're seeing, right? But, if you get rubidium and you give it enough energy of electronic transition, is that it emits this beautiful kind of, it's hard to describe the color of red. It's kind of, I would say that, a purplish red, but not quite a burgundy, but there's just something that's really beautiful color. So while rubidium itself, you're like snooze fest, right? In the physical appearance of it, there are these dynamic, we can do emission spectrum. It's one of the ways we can characterize all the elements in the periodic table, or what are the unique electronic transitions. And some are in the visible range that we can see pretty clear. As fireworks, you're looking at emission spectroscopy. Yeah. And luckily there's beauty parts you can see, and we can make green and yellow and purple and red and really fun stuff. And so even though we might look at the elements and be like, boring, is that if we put a little bit of energy in, which is what I love too about the game, is they got the currency right. Like, there's no such thing as a free lunch. Everything costs.
Yeah.
Right?
Actually, there's this other conceit in the game where energy is not created or destroyed. It just gets moved around the board. Except it's not true for one specific reason that I think, there's one circumstance in a 2-player game where you actually get to get some new energy out of the box.
I think that's just because there's not enough energy floating around with only 2 players for that to work. But honestly, that's such a bad call. Most of the time, we never even used that move because it's like just getting 1 energy for that is just such a bad choice.
See, I think at that point, the game should just explode, and then no, a physicist should just pop out and go, no.
Yeah. So actually, I've got some question about some of these oddballs you mentioned. So you said how in these families, there's always the black sheep, the weirdo one. So there's some ones I know. So
that's a judgment. I shouldn't be that judgmental, but I am.
No,
okay. They're weird.
Yeah.
Let's point. I'm pointing right at Mercury here. It's like liquid metal, room temperature. What is going on there? What about that combination of that family and that row? How on earth do you get something that is a liquid metal at room temperature?
But you also got gallium, which is a liquid metal at slightly above room temperature.
Right. The minute you put it in your hand.
Yeah.
Right.
I want to get some gallium. I want some gallium. Yeah.
And I think again, but they are it's no one else in their family. That's it. Right. And so doesn't that that is, people, and I am not in a metallic or transition metal chemist or heavy metal chemist, but I could see why people would be absolutely obsessed with mercury or gallium, to be like, what is it isn't even within its family. Yes, there are shared traits, but even within its families, it's the one that is doing what's happening here. Right. And then the unique properties that unfolds. To me, besides the liquid mercury is the high cohesion, right? You quote spill mercury, you pour it, it's like little ball, and it just rolls around, and you're just it has a lot of cohesion between the atoms, where it's not like if you pour water, what a mess, right? It spreads, it wets the surface.
True.
There is this also chemical interaction where the mercury is
it's not touchy-feely. It does not like to touch other things.
It does not like to wet, and I there isn't this kind of distribution of that matter across a large surface area. It's actually like, no, we don't like to hang out with you other people. We want to be by ourselves. And so like, those are some interesting features. But again, I would come back to every family has, and again, I'm putting my own, but that's how we can understand the periodic table is what are these groups, families, and there's so many circles of connectivity where even when, and oftentimes across the rows, people very much focus on columns, but then when we look at big blocks of behavior, like even we mentioned earlier that lanthanides and the anthracite and the lanthanides, right? That's a row. That's a different way. They do have shared behavior, and there's a whole group of chemists that are transition metals, but then their subset is, but we're first row transition metal. So
I guess everybody's got to have their little niche on the table, huh?
Well, it turns out that there's unique behavior with that first row transition metal. So what we're finding out is even in the 100 plus odd years we've had what we would think is the structure of the periodic table is that it also reveals what some of the genius was of bending them in their behavior. We're still learning about the elements. We're still deciding that, hey, yes, there are the column behavior, but there's also row dynamics, but there's also this bigger group behavior that we see. And so I think that's what I also liked about the game is that it tries to get you to get a bit of exposure to, hey, there's a lot of property. There's a way we can group these things, not just by columns, but we also have to talk about what are some energies involved, right? Where they're kind of located. And I think hopefully it gives people an idea of this table is organized, yes, by atomic number, right? But the more important thing, at least as my opinion as a chemist, is that it's organized based on function. But as I'm sure as a biologist, right away you should be like, and that's structure, right?
Yes.
And at this stage, though, it's structure at the atomic level.
Yeah.
So you're looking at both. It's just jam-packed full of information on the periodic table.
There's a reason that the periodic table appears on napkins and shower curtains. And it's probably one of the most beautiful representations of science, right? One of the real victories of science is the periodic table.
We got good branding.
Yeah. Great branding.
And
great branding.
We did a good job with the color coding.
Yeah.
I feel like that's the other thing is like if we make it color coded.
It's like I think we talked about how the Erlenmeyer flask is the most sciencey thing. DNA, the periodic table.
Yep. There are just certain symbols.
These are the lucky charms of science. Well, we've touched on this a little bit, but I did want to ask, you said the first column transition metals. So we've got yttrium, which I know is one that you obviously like because you use it in your social media, and then scandium, and then you jump down and those two boxes expand out into entire rows. And like you've got some interesting players in there, like uranium, neptunium, plutonium. Why are the actinides and lanthanides in quarantine in their own separate space on the table? And how do they relate to yttrium and scandium, which are not?
If you look at the atomic number, right, you jump from barium, which is group 2, and you see a 56, and you're like super, and then you go right down. Radium is that, quote, last element in group 2, and it is 88. And then all of a sudden you move to the transition metals, which is right next door, and you see that, okay, number-wise, you like, okay, 57, 89, and then you move again, and you're like, am I going insane, or is that... It goes 57, 72.
Yeah.
It goes 89, 104. Now, I'm sure that there are, people will say, oh, there's good... They wanted it to be rectangular.
Yeah, they wanted it to fit on a page.
It's a space-saving move.
Yeah.
Fit on, which makes us, fit on a single printable sheet. And sometimes, depending on who's produced the periodic table, like if you look at the NIST periodic table, or one of the great versions, which is one I use a lot in my classroom.
And NIST is like National Institute of Standards and Technology?
Yes. Okay. So NIST is National Institute of Standards and Technology, is that they actually do this cool thing, which they show the ribbon effect of after barium and radium, because where it's split is also very interesting, is that some periodic tables will split it at LA, and AC.
Yeah.
And what the NIST periodic table does is it's actually shows you a ribbon that kind of floats from the two, and then the ribbon connects it to the lower, so that people will clue into the fact of no, these should actually go smack right here, which would push the periodic table
way longer.
Way like a baguette.
Yeah.
Long and thin.
And so it's a space saving move. I mean, it makes sense printing wise and kind of to condense it. But what it does is sometimes almost out of sight, out of mind.
That's very true in this game, which we're going to come back to for the nitpick section.
And I have a question about this, actually. So you mentioned how the structure of the periodic table is due to the structure of the elements. And I want to confirm if I've got this in my head right, because I seem to remember from high school chemistry, the reason why you have the jumps where you do, why you have the number in rows, is because it's not the protons so much as it's the electrons that orbit around them. It's like the first layer you can stick electrons in only has space for 2, which is why there's only 2 elements in the first one. And then the next layer can hold 8.
So we have a numeric order, which would be why if you count over, you should have, goes up by 1. But you're absolutely right, where then you can get to the principal quantum number. And if you count down, where you will go 1, 2, 3, 4, and that is the 1, like you would say with, and orbitals are not actual physical locations. They are probability distribution maps of where the electrons should be.
We are not getting into quantum mechanics this episode.
No, that's we gotta find a different game to talk about that for sure.
But that quantum energy level is sometimes on the periodic table that again is so jam-packed full of information. But besides the group number, which would be across the top left to right, there are numbers that go from that first row right down, and it's 7. And remember that the lanthanides and the anthonides are actually 6 and 7 because they slot back in. Those are the energy levels, right? So like when you talk about electronic configuration, which again is our construction of trying to organize spatially where are the probability distribution maps, is we say that you have the lowest energy to the highest energy, so 1 through 7. And that's also, that great organization is also telling you about, okay, where spatially these things are. So there is both organization on the entire atomic level, right? Where we talk about where the 2 big subatomic particles that we tend to spend a lot of time on, which would be proton number and electron number or electron density. That's it's a fun, when you look at it, we often, again, focus on atomic number, but you're absolutely right. It is also telling you about electron density, which gets us back to the trend, right? Because you're talking about ionization energy is one of the big trends. Atomic radius, which has to deal with both, the interaction, right, between the pull of you have all these electrons which hate each other, but also are attracted to this dense positive core, and then the more you add and the more, then you get this kind of size. So you actually have a couple different properties that are dealing with the fact of you have to look at the holistic approach of the atom. You have to look at the protons, the electrons. You have to look at the interplay between them. If you try to remove them, if you add more, if you have less. And so that's what you're looking at.
Do we have to look at the neutrons or can we just ignore the neutrons?
No, I love a neutron moment because they're sly. They're very massive. I love that because they're sly. They're just like, we don't have a charge, so we're just going to be over here. They're massive, the electrons are puny, but they're negative, so everyone focuses on them.
Yeah.
They're also important in bonding. I shouldn't dismiss them, but but the neutrons, right? You get isotopes, which are so critical, and so telling. I love isotopes because they are snitches.
So can you define what an isotope is?
Wait. I want to jump back and then I want to come back to neutrons. So we've got the atomic number is the number of protons, right?
Yep.
But the number of protons determines the number of electrons, and all chemistry really is about those electrons, right? And where they are and how. No, are you serious? It's not the electrons?
Or
I
we
mean,
were just saying,
you want to reduce an entire field to one subatomic particle? Is that you
Is
want to
that not?
fight? Is that what we're doing? Are we
Is that
choosing
well, okay?
violence?
Okay, let's do it this way. What percentage of chemistry is defined by the electrons?
I wouldn't even, but that's still trying to reduce it down to a single particle when really we got to talk about relationships. It's
Okay,
the
I guess I'm breaking
relationships
the whole thing that you
between.
just said about the holistic nature of an individual atom is electrons are important, protons are important, neutrons are important too.
If it was just electrons, like that doesn't get us to why do certain bonds form and others don't.
Okay. So the
Right. I mean,
covalent
electrons,
versus
I'm not saying they're not important, but we
yeah,
can't ignore that there is a lot of other stuff going on. We see that with ionization energy, there are trends, right?
sure.
If you, the first group, removing that first electron, relatively easy peasy. You try to remove the second electron, though, we're going to fight. That is, the energy cost jumps enormously. And that's because you have got, the force, right, of all that positive charge. Now you've removed an electron, but what's actually happened too is that attractive force between those subatomic particles is actually even more like trying to remove a second electron. That energy cost is prohibitive. And anyone who plays the game and wants to try it, I'm not even sure you can do it because it's like a first ionization. It's just going with first ionizations across the trend. But as students will recall, if you try to remove from lithium the second electron, good luck. Right? I mean, you can do it, but it is going to cost you an enormous amount of energy. And that is not only about the electron, that's about the pull of the nucleus is now that attractive force because you actually have more positive than negative as you've tipped the balance. And now we're pulling off the second electron is much harder. Is that just an electron problem? Because that sounds like that's an atomic.
Yeah.
and I've got another one that I learned at DragonCon this past year. And Rachel, I don't remember if you were on this panel. So we talked about isotopes, which is where you have extra neutrons or fewer neutrons in the nucleus. Apparently, if you use heavy water, so
Yes.
water where the hydrogen has extra neutrons in
Yeah.
it tastes sweet.
What?
It
Yeah.
actually changes the flavor of the water because it changes some interaction of like the way the water
Receptor.
behaves and how
Yeah.
it affects our sweet receptors.
I think
Yeah,
that
so-
our sweet receptors are broken. The number of things that are not sugar that taste sweet. I mean, artificial
Well-
sweeteners, water, lead.
Yeah.
I mean, come on.
But I think that again, that tells you, right, the bait and switch. But I think so isotopes are, you have the option of differing numbers of neutrons and you can get to heavier. We often say that, okay, and it's about probability. What's the one that's most frequently occurring? And then you might have a soupçon of others, although there are some elements where it's nearly, it's actually like a 2/3, 1/3 or a 50-50 split. But so you have those kind of variety and with water, again, taste is perception. So you gave people that and you asked them to rate it. So part of it is perception. And I'm sure all of the people doing human studies trial, when you ask people those questions, that's got to be done in a very specific way. But the science of it is, that even that slight change in mass and how, the compound and the receptor interact, there is this potential that you have this difference in how it's perceived by the taster. Now, most of the time with isotopes, especially forensically, what we can kind of use them for is because we have mapped out, we know so much about the statistical portion, right, of all of these elements and their isotopes. We've also mapped out the world in a lot of isotopic abundance for some key elements like oxygen, hydrogen, carbon. And the proportion, say, in different ocean waters, in different soil types, in different parts of the world, and also different elements like strontium, that it can actually be really helpful when you're trying to link up where did this come from in the world. And one big way that it's used in forensics is identifying, say, there was a really great special issue in a forensic science journal about identifying civilians and combatants that were involved in kind of actions in World War I. And they had a lot of, unfortunately, huge mass graves, right? Large numbers of casualties. But then trying to match people up now when we have the technology to do so, to do identification. Sure, we have DNA we can get, but you still have to then I still need enough information to get a standard from a living family member. You've got to narrow it down. If we literally are looking at this open grave in Flanders or something, and you're like, well, where are the combatants from? Where should I even look to get this information? So they were using isotopic abundance to say, hey, in the formative years, when your bones are really growing and forming and you're really taking uptake of those elements, certain key elements, turns out Canada, right? And not only Canada, but a particular region of Canada, they were able to identify going back, well, we need to go to the Canadian Armed Forces. And we need to say, okay, who was in this part of this country in this time? And that so helped narrow it down, right? That they can then say, have a discrete amount of samples they can collect with DNA and say it needs to be Canadian Forces deployed here from here. It really helps narrow it down because of we have so much information on the probability distribution of those elements. So to me, isotopes, they're the MVPs. They help us track so much stuff forensically. I have a special place in my heart. There's certain elements that denote that, hey, you had a lot of seafood or access to kind of sea-based stuff versus, oh, you were probably having more of grains and then grains, where do we get most of those from in this country? And then if more cattle or more beef. So even that can still be really helpful and help kind of point to what do you have access to? Sometimes, mostly again, your really formative years when the bones are really on the uptake. And so that can still be really helpful. It's super helpful too with tracking. This is going to sound weird, but linking together drugs, drug shipments, certain, right? If you're growing, say, like cocaine, natural product, even if it's purely synthetic, what was the water source used for that synthesis? What were the solvents? Where did they purchase some of these things from that could still, and if you're trying to link up, say, a particular to see, is this all the same kind of manufacturing chain? You're not even trying to perhaps localize it to where in the world is carbon sandy. No. You're trying to link it up
Notorious drug lord carbon sandy.
Yeah, that I did not say that. Do not come for me, Disney or whoever conglomerate. Are these batches produced in a very similar way where they, this huge distribution, is the kilo found here, is it chemically linked to the kilo over here?
Interesting.
Right. And so that kind of information, besides just a good general chemical scan of what compounds and what proportion, the isotopic abundance can also be very revealing about what are the water sources, what are the solvent compositions that might have been employed. And so, that's why sometimes I joke that isotopes are snitches, but I mean that in the best way.
So isotopes, same number of protons, increase neutrons. And I think I've had this explained that like biology is lazy and will favor the lighter version of that isotope. So you'll see accumulation of lighter carbon, for instance.
I think that depends because one of the things I think Raychelle was mentioning is you can tell like carbon source. So corn uses a certain type of photosynthesis different from like wheat and rice, and they end up with different carbon isotope ratios from that. So you can tell if you had a more corn-based diet or more wheat and rice.
Yep.
And I know here in the U.S., it turns out that we're all eating secondhand corn because most of the corn we grow is actually fed to animals, pigs and cows and chicken. And so we're getting all like our diet. When if you're here in the U.S. and you're eating beef or chicken or pork, you're probably actually eating corn-based stuff as opposed to some other, and you can tell that in the ratios of the carbon that are in your body.
Yeah, and also in food fraud, it's a big thing. Butter from grass-fed cows. And you're like, first of all, this better be butter and not margarine because we have real strict laws on that stuff, right? But also, you've said a certain type of feeding for this cow. Well, isotopes will,
Interesting.
will really clock that. And so it's become a way that
listeners didn't see this, but she did the whole like point at her eyes, like I've got my eyes on you.
I got my eyes on you, right? So isotopes will help us get real ideas about sources of stuff, but it all comes back down to probability. We have low probability, we have high probability stuff. And that's why, getting these backgrounds, you've got to have a good set of what is the probability for just like this area, this background. They've also done this with we saw in certain parts of the world historically, like lead pipes were and I mean like Roman, right? Like they were like, oh, the fall of the Roman Empire, which by the way is never on my mind on a daily basis, but the Roman Empire. It's because there were so many lead pipes, or like, there's if a historical person was poisoned, you're like, oh, it's arsenic. Well, you also have to get the background of where was the person at, because there's actually arsenic just that appears in your person. There's also, if you're buried in the ground, what was the soil? Did it leach in? And so one of the first things they'll do is, okay, well, what's the background? Here's the target of the person we think is poisoned. Sure. Now get samples from everybody else in the graveyard. Well, not everybody, but some proportion, right? And then what's the background? So you can get, okay, is this actually a signal? Is it actually significantly greater?
Gotcha.
Or is this just like the norm?
Awesome. I think we should probably start wrapping up at this point. I did want to ask, Raychelle, do you have a favorite board game that you like to play?
Yes. Well, I grew up in a family that played board games, but I'm going to go super retro, and I'm going to go with Monopoly.
Okay. All right. We haven't had anybody say Monopoly yet.
And I'm going to say Monopoly because my family, we would play Monopoly, and Monopoly, like we would be like, we're never playing this game again, because we would always fight. It never went well. It really reveals a lot about how greedy people are and how closely they will bankrupt you. But on the other hand, there was just something about that game that it was wild. Like I had some of the funnest nights was playing and just realizing how crafty, especially I'm like, my mom is vicious and she is the nicest lady I know. But she will be like, I love you. I'm taking all of your hotels.
Actually, let's move into our nitpick corner, because I think it's time for that. This is where we do, well, actually, or this isn't quite right, or we love this game, but. So, Raychelle, go. You have something teed up, I can tell.
Well, part of it too was the groups they chose. Like they're called goal cards?
The groupings cards of elements.
Yeah.
The groups of like 2 or 3 elements that have some common theme to them that help you collect points.
Yeah, like toxic. Yeah, just something that connects these in terms of how we use them.
Yeah, I think, but again, I mean, I was like, these are the ones that you can. But that's, but also I just look at the periodic table based on I'm an analytical chemist. I'm a forensic chemist. I look at it in a different way, as we all should. So that's a very petty kind of thing. But also, again, they booted some of the coolest elements. They were like, we don't want these ones down here.
So, no, I know. Literally, uranium is not on the list. Uranium's not in the game.
How?
That maybe they were saving that for the expansion.
Maybe.
Like the trend now is that you release a board game and you already have the first 3 expansions planned. Maybe they have the Lanthanite and Actinite expansion.
Then that is flip the script, and I'm like, brilliant. Because I would get it just to be like, is that an expansion pack 1? Like, that would be so cool. Also, the wraparound. There's only one trend that lets you wrap around. They were like, you can't do that with any of the other trends. And I was like, watch me.
Yeah. So my nitpick is a little bit related to that, and just has to do with the gold cards, because we noticed this as we were going through. The elements are not represented equally.
No, not even
some
close.
Elements show up time again and again and again, and some elements you'll never see on a gold card. And I just realize there's only so many things you can make groups of that your average consumer would actually recognize, but it still would be nice to have those spread out. And it did feel like the difficulty of collecting the goals was not correlated to the number of points you got. I didn't do a thorough investigation of that, but it seems like it should be like, okay, the harder goals, like goals difficulty 2, 3, and 4 all require 3 elements each. So it should require like more moves to get the ones at level 4 than at level 2. And I assume there are, but it didn't really feel like there were definitely times where like, oh, in this one turn, I can collect the level 3 gold just with my normal moves.
Some of those gold cards were weird. It was like the element in its group with the lowest heat capacity. It's like, you say that these are things that average people know. That is a weird, like I had to look that up. It's like, what does that mean? It's like, I know water has high. Anyway, my nitpick is similar to Raychelle's, is the exclusion of the lanthanides and the, I'm saying actinides, but that's not right, is it? How have you been saying
do not go with me.
All right. Sorry.
I think we've determined that elements are like dinosaurs. It doesn't matter how you say them.
There's not an official pronunciation guide. That may very well be true. The thing is, okay, I understand the utility. I understand why they did it. I still think they have a booklet, like all Genius games, the science in the game. It would have been very easy to put a full periodic table in there, and they didn't even put it there. It's like, your game is periodic. You got the periodic table. Just show one periodic table where you haven't excluded these. Do you know what I mean? Just take one page. Yeah.
And I would have liked to see some go cards. I mean, again, this is just a judgment call, but if you're using this game in a classroom or in some kind of a science camp thing, I think a fun thing would be like, what is the expansion pack that you would build, right? Because then you might have people be like, you know what about like, I move diagonally. It's like, yeah, but if I want to move along the metalloids, you're going to have to do a diagonal move. Like, what's some new rules and what's a new expansion pack? Like talking about, your things that are naturally liquids at what we define as ambient temperature, things that are gases. What is the fun expansion packs and groups that they would come up with? Like, what are your biologically significant, sometimes there's tons of elements on the periodic table and, you get to biology and you're like, these 7. But it's more than 7.
Basically.
It's more than 7 because then you prime people to think like, and they're surprised when you have zinc that shows up and is critical, right?
I mean, it's CHON. It's carbon, hydrogen, oxygen, and nitrogen.
I know.
Phosphorus
you're like boring. Like, it's like going to Gap and getting khaki pants and a black shirt. You're like, again? You're like, ooh,
but
what
they're
a
the
new
Lego
look for the
bricks
Gap.
of everything.
But there's a reason for that. What are the fundamentals, right? What are the key things you have? And
either
then
new rules or new goal cards would be really fun, right?
Yeah,
just like, hey, come up with some new goal cards.
New goal cards, what are different trends? Maybe there are people that want to talk about, hey, what are some different trends? And I think that's the fun thing about this game is even when you're critical about a game and people are like, well, I would have done this, well, then do it then.
Yeah, for sure.
Then you come up with the modification because then, especially in a teaching tool like this or even a fun game, in order to come up with an expansion pack, new goal cards, new rules, that means you know a hell of a lot about it. And that's my master plan to trap you into learning chemistry has in fact succeeded.
All right. Well, I think this is, again, Raychelle, you are wonderful at helping us transition between sections as the conversation just kind of goes. But why don't we move into grades? Because I think we're talking about what we like about this game. I am happy to go first. I think that for the science here, I'm trying to decide how much I want to ding it for the actinide lanthanide thing. And I think I'm going to, I'm not going to dock it. I think that the intentionality is there. I think that the practice using the periodic table, because that's really what this is. The periodic table is our game board. We've had other games where the periodic table was just where you kept track of your score. Here, it's all about the periodic table. And you learn a lot about the periodic table just by playing the game. You got to, when the new goal card comes up, you're like, okay, where is this element, right? Like, without even realizing it, playing this game, you are practicing and familiarizing yourself with how the periodic table is laid out, where things are found, how they relate to one another. I have no issue giving it an A on science. I think for fun, I did enjoy it. It's quick. I even beat Jason by 1 point, which has never happened before in the entire gaming with science. Every game that we've played, with the exception of one bonus episode, this is the first time I legitimately beat him by 1 point. So it should be more fun for me for that reason. But actually, no, I'm still probably just going to give it a B. I don't think this is going to enter into my regular roster.
Yeah, I'll agree. I will agree with both those. I will give it an A for science. I think that it represents what it wants to represent well. I think you can't play this game without learning about the periodic table and chemistry, including the grouping developments for the goals. I think is an interesting thing. It helps you think about some stuff. Also, just the trends of like, oh, if I move this direction, that is increasing ionization energy. If I move this direction, the radius gets bigger. Like these properties of atoms that I don't usually think about because I'm not a chemist. You can't play the game without becoming familiar with them. So I think A for science is perfectly fine. I'd also put it a B for gameplay and fun.
Because I beat you?
No, actually. So it's like, just because when I played it, and I did do a little like test run myself before we played it together. And both times I felt like once I was like 4 or 5 turns in, it's like, okay, I now understand the game. Now it's just the process of playing it out. felt like the strategic depth of it that I usually go for games is not quite there. I'd, again, put it as B. I would not be opposed to playing it, but I'm probably not going to go for this as my choice pick.
I think this is an excellent game for the classroom. I really do. Easy and quick to learn, quick to play, and like really just without even realizing it, you are learning about the periodic table. You have to.
Now, Raychelle, what do you think?
I'm going to go with a B minus.
Oh, wow. Okay.
Cool. Oh, the chemist has weighed in.
No, but I think what I found, yeah, sure, there's the missing parts of the periodic table. But I was like, why is this called an academic track?
True.
But also like the go cards. But that, I'm just like, but that gets to a personal preference. That's not really about the quality of the game. There are other games that are very popular that I'm like, not for me, right? Like, so, but what I could see and what I would give it, I would move it into the A category, is that there is using it in the classroom and then giving students the freedom to modify and expand the game. Because I think that the potential of the game is for them to do what we're doing, is to really be critical, to think about gameplay, but also to think about how would I modify, revise, expand, correct. And I think there's a real useful power in that.
So as a lesson coupled to critical peer review, this would be an A.
Yes. And I think that part, and also, can we talk about the little, I love an Erlenmeyer flag. I love like the game, like the tokens and the energy. I think the energy tokens too is everything costs, right? Like, there is no, so there is a lot of parts that I like. So maybe I am maybe I agree with my students. I'm a harsh grader.
Maybe this should be a B and not a B minus.
I know I think you're right. I will modify. Look at me. Look at the growth. I will say it should be.
You haven't had a chance to play it yet. So did you want to try to give it maybe not a fun, but interested in playing?
I watched the videos about the gameplay.
Yeah.
I think actually I would like to play the game because I'm wondering if some of my harshness is because of just trying to wrap my head around about like, this seemed kind of a bit awkward about, wait, there it goes, there's a chicken. And I'm watching it being played is very different than being in it and actually having the tactile experience.
All right. So we need to wrap up. Raychelle, where can people find you?
You can find me on the crime-ridden streets of DC. No, it's not. We're at a 30-year low, everybody. But no, you can find me on social media, Radium Yttrium, and also Dr. Ravidium on TikTok.
And you also write for, I was looking on your TikTok, it links to some opinion pieces.
Yeah, I write a column, a forensic science column called Trace Analysis, where if you want to learn more about, like, I literally have written about like isotopes helping crack a butter fraud case. and vampire DNA work in a graveyard. Yes, it is true. Salem witch trials. So what's the forensic science there? So check out my column at Trace Analysis at Chemistry World for all things creepy science and crime ridden.
That's awesome. And then do you do Dragon Con every year?
I have been doing it every year. So I was on that panel, Jason, about the weird kind of physics things, which was kind of fun because I'm like, how am I on this column, on this panel? But yes, I plan to be back next year doing more weird stuff.
All right. We're trying to collect people from each of the tracks at Dragon Con.
That would be awesome. Yes. Okay. Yes.
All right. I think with that, we should probably wrap it up.
So fun to talk to you guys.
Thank you for joining us. I hope you have a great month and great games.
And as always, everyone, have fun playing Dice with the Universe. See ya.
This has been the Gaming with Science podcast, copyright 2025. Listeners are free to reuse this recording for any non-commercial purpose, as long as credit is given to Gaming with Science. This podcast is produced with support from the University of Georgia. All opinions are those of the hosts and do not imply endorsement by the sponsors. If you wish to purchase any of the games that we've talked about, we encourage you to do so through your friendly local game store. Thank you, and have fun playing Dice with the Universe.